Hello students, welcome back. We completed up to section 2. Now let's go to section 3, homomorphisms and isomorphisms. But it'll turn out section 3 is very simple because everything here is an analog of what we already did in group theory. First, let's define a ring homomorphism. A map phi from one ring to another ring is called a homomorphism, or ring homomorphism to be a bit more specific, if it preserves both ring operations, both the addition and the multiplication. And then we use the same terminologies: monomorphism, epimorphism, and isomorphism. If the homomorphism is one-to-one, then monomorphism. If it is onto, an epimorphism. If it is both one-to and an onto, then it's called isomorphism. Furthermore, if the homomorphism goes to itself, we call it endomorphism. And if the endomorphism is one-to-one and onto, so it's an isomorphism as well, then it is called automorphism. Well, the same terminologies. Furthermore, we can define images, preimages, and kernels pretty much the same as in group theory. Also, the same conclusion holds. Under a ring homomorphism, a subring S of R is sent over to image phi of S in R prime, but the image is also a subring. How do you prove that? Well, that's left to the students. You can do pretty much the same thing as you did in group theory, except that you'll have to do it twice. One for this and one for that. Good luck. And then we can establish the same thing for preimages. If S prime is a subring of R prime, then the preimage of S prime, and it's not the inverse map phi inverse, it's a preimage. Preimage of S prime is a subring of R. The proof, well, pretty much the same as the corresponding theorem in group theory. So I'm going to leave you there. The details are left to the students. Now, the final topic here, kernel. The kernel is a preimage of the additive identity, 0. And here I use 0 prime because it came from the ring R prime, but very few people do this. Let's just use 0. In any case, the additive identity is 0. Yeah, for simplicity, we can write like that. And that kernel. So any element of the domain that is mapped over to 0, and set of all those is called kernel. And then it turns out the kernel is a subring of R. Yeah, that's pretty simple because it's a preimage of a trivial subring, so no problem there. But here are some interesting properties. Its left and right cosets under multiplication are both equal to k. You end up with this property. So xk or kx are both equal to k. And the proof is actually pretty simple because what are the arbitrary elements of this coset? Arbitrary element is x times some element of k, right? Arbitrary element is of this form, x times k form. And then, does it belong to kernel? You can check. Phi of that is phi of x times phi of k. And what is this? That's phi of x times 0, isn't it? And if you're a purist, you can use 0 prime for the additive identity in R prime. Anyway, it's 0. And of course, I'm not a purist, so I'll just remove prime. All additive identity, I'll write it as 0. And then you can do the same thing for arbitrary element here as well. You're going to get 0 times phi of x is 0. In any case, we have this proof. So the conclusion, the left coset xk and right coset kx, they're all equal to k. And a subring with this property is called an ideal. It turns out the ideals play a role of normal subgroups of group theory. That is, we can define cosets like this under the addition. Then it turns out this quotient set is a ring. You see, you can define this coset under the addition using the left coset relation, which is a equivalent relation. Yeah, you can prove all that. And then you can consider the set of all equivalent classes, and those equivalent classes are actually cosets. So we have a quotient set, but does that quotient set have a ring structure? Yeah, we know that it's a group structure with respect to the addition, because under the addition, rings are abelian groups, and every subgroup is normal in abelian. So addition is well defined, no problem there because it's a factor group. Is multiplication also well defined? That's a problem, and that's where the ideal condition will be used. Want to see a proof? Well, here's a proof. This one here is simple, and this one here, that's going to be a big deal. Well, not that big a deal, but that's giving me a bit of a work. Let's see, how about this one? X plus k plus y plus k, this basically arbitrary element here is of this form, x plus k1 form plus y plus k2 form, and then that can be written as x plus y plus k1 plus k2. But then again, that's x1, x plus y plus a certain k, because k is a subring, so it's closed under the addition. And then you can prove vice versa as well. Take arbitrary element here, and then you can consider, okay, all right, take arbitrary element from the right hand side, x plus y plus k, and then you can rewrite it as x plus k plus y plus 0, because 0 always belongs to every subgroup, and then that is as a matter of fact, I skipped a step. Here, this can be written as x plus y plus k plus 0. Okay, all right. You can do 0 plus k if you want to, or k1 plus k2, that'll add up to k. You can find anything, that's fine, but easiest one I can find is k plus 0 or 0 plus k. Anyway, we get x plus k form, so that belongs to this, and y plus k form, that belongs to that. Okay, that proves this. Now, how about this one? How about that one? Well, all right. X plus k1, y plus k2. An arbitrary element of the left-hand side, that can be x, y plus, let's see, x k2 plus k1 y plus k1 k2. Did I do this right? With respect to the addition, we have commutativity, but with respect to the multiplication, not necessarily commutative. And then what is this? X times Y, great. And then X times K2, wait a minute. It belongs to the left coset, so this is going to be a certain element of K. Which K? Let's see. Let's keep K2, but some other expression like K2 bar. How about this? K1Y, it's in right coset, but that's the same as K. So what expression shall I use? I'll use same K1, but K1 bar. And then K1 times K2, okay, that's fine. K1 times K2. And then let's see, let's put parentheses here. And then please note that this is X times Y plus a certain, oh yeah, I don't need it. I don't need anything here. K is a subring, so this entire thing belongs to K. So arbitrary element of the left-hand side belongs to the right-hand side. And then I can do the same thing from the right-hand side as well, and decomposing accordingly. As a matter of fact, I wrote the abbreviated version with proof like this using the color coding. Just use set operation. Any element of K plus any element of K, like that. Same goes over there. So what did he do here? And we established the fact that we can consider factor rings or quotient ring just like we did factor groups. But the condition for factor rings is ideal condition. That's a little bit different from the normality condition for group theory. That's the only difference. Otherwise, pretty much the same. By the way, we just proved the kernel satisfies this, yes, and consequently we can consider factor rings for kernels, but by doing these, you can prove, as a matter of fact, any ideal will generate a factor ring. So it doesn't have to be a kernel of any homomorphism. Just any subring with this property will do. And that's a part of thing we are going to do in next lesson. But for now, we'll say we are done with lesson 11. Homomorphism, isomorphism, they're all analogous to what we already did in group theory. So that's about it.